Good morning all. In yesterday's class, we have started the 8086 architecture. So where the entire architecture of 8086, all the entire architecture of 8086 mainly divided into two functional units. It is mainly divided into two functional unit, bus interfacing unit and execution unit. And we have also discussed the individual functions of the execution unit and the bus interfacing unit. So where the bus interfacing unit, it fetches the instruction codes data from the memory or IO devices. And then it executes the instructions, and after executing that instructions, the result will be stored in the memory location, or to the result can be sent to the output device here. Whereas the execution unit, it receives the program instruction codes from the data, program instruction codes and data from the bus interfacing unit, and then it executes these instruction codes, and then the results are stored in the general purpose registers. So the bus interfacing unit fetches the instruction codes data from the memory, and after executing that instruction, the results are again sent to the memory location or to the output device. Whereas the execution unit, it receives the program instruction codes and data from the bus interfacing unit. So after that, it executes instructions and store the results in the general purpose registers. So we will see the individual details of the bus interfacing unit. So here you can see the functional block diagram of the 8086, so which describes the entire architecture of 8086. So the architecture is internally divided into two functional units: bus interfacing unit and execution unit. So where the bus interfacing unit, in turn, it consists the other functional units, and the execution unit also consists the other functional units. So we will see what are the parts of the bus interfacing unit, or what the bus interfacing unit contains. So the bus interfacing unit contains the segment registers. It contains the instruction pointer register, address generation unit, instruction queue, and bus control logic. So from the architecture diagram also, you can see in the bus interfacing unit, so from the bus interfacing unit, you can see the segment registers. There are 4 segment registers and an instruction pointer IP, and the bus generation unit, that is the address generation unit, and instruction queue, and bus control logic. So these are the functional units inside of the bus interfacing unit. So we will see one by one detailedly. So here the first one is the segment registers. The 8086 bus interfacing unit, it consists the 4 segment registers. The bus interfacing unit, it consists the 4 segment registers. So they are the code segment register CES, data segment register DS, stack segment register SS, and extra segment register ES. So the bus interfacing unit consists the 4 segment registers, and all these segment registers are 16-bit registers. Okay, and the size of each segment register is 16-bit register. The size of each segment register is 16-bit. So all the 4 segment registers are 16-bit registers. And here these segment registers are combined with the the base register of the execution unit to allow the microprocessor to address 1 MB of the memory space. So the registers from the bus interfacing unit, they are combined with the registers from the execution unit, and so the two registers define the 1 MB of the memory space. It defines the 1 MB of the memory space. So how these two 16-bit registers, so they determine the 1 MB of the memory space. So we will see it. Okay, so here all the segment registers, so here the segment registers are combined with the base registers of the EU to generate the 1 MB of the memory space, or they will allow the processor to address up to the 1 MB of the memory space. And here within the 1 MB of the memory space, so the 1 MB of the memory space is the memory capacity of 8086, because the 8086 has a 20-bit address bus. It has a 20-bit address bus. Okay, so the 20 address lines are A0 to A90. So using these 20 address lines, the microprocessor can address up to 1 MB of the memory space, that is 2 power 20. So that is 1 MB of the memory space. That is 1 MB of the memory space. So now the total memory of the processor is 1 MB. So within that 1 MB of the memory space, the 8086 defines 464 kilobyte of memory blocks called code segment memory. So code segment memory, data segment memory, stack segment memory, extra segment memory. So these are all the memory blocks here, and each memory block is a size of 64 kilobyte. So within that 1 MB of the memory space, the processor defines the 464 kilobyte of memory blocks, and so here each block of these blocks, each of these blocks, they are used for different purposes by the processor. So the 1 MB of the memory space, within that 1 MB, it is defined 464 kilobyte of memory, and that memory block names are same as of the segment registers. Okay, so the bus interfacing unit has 4 segment registers. They are named as code segment, data segment, stack segment, extra segment. So that is one point. And here the other point is within the 1 MB of the memory space from the 20-bit address of the processor. So within that, so 464 kilobyte memories are defined. So they are named as code segment memory, data segment memory, stack segment memory, and extra segment memory. And all these blocks of memories, they are used differently by the microprocessor. They are used differently by the microprocessor. So we will see, so what is the function of each memory block here. So the first one, if you take the code segment memory block, so the code segment, it is used to hold the program instruction codes. The code segment is used to hold the program instruction codes. So when you are writing the assembly language program, so you will have the mnemonics. You will have the mnemonics. So for every mnemonic of the instruction has a equivalent machine code. So all these machine codes, they are stored or they are placed in the code segment memory. And the next memory block is data segment memory. So from the name you can understand that, so this 64 kilobyte of data segment memory, it is used to hold the data of the program. So for every program we will have data. So we must specify data to the program. So all that necessary data to the programs, all the necessary data for the programs they are stored in the data segment memory. So the code segment memory, it is used to store the program instruction codes, machine codes. The data segment memory, which is used to store the data of the program. And third segment memory block is stack segment memory. So mainly the stack segment memory, which is used to store the interrupt addresses, subroutine addresses, and return addresses of a procedures or subroutines. So we know what is a procedure or subroutine. Generally, the subroutine is defined as a group of instructions. They are defined separately from the main program. I mean that, so there are certain instructions, they are written separately from the main program, and that instructions are repeatedly executed to perform a similar task, to perform this same task. Okay, so the stack segment memory, which is used to store the interrupt locations, subroutines addresses, and return addresses. So mainly it deals with the stack operations. And the fourth segment memory block is the extra segment block. So here the extra segment block, which is used to store the extra data. Extra data in the sense, suppose you have a string of data or you have an array of data, say. So you have a large data and you are defining such large data in terms of arrays. Okay, a group of data. So such a big data or large data, so they can be stored in the extra segment memory. So these are all the 464 kilobytes of the segment memories: code segment memory, data segment memory, stack segment memory, extra segment memory. Okay, so we have 4 segment registers. They are 4 segment registers. They are 16-bit registers. Okay, and so the segment memories are 64 kilobyte of the memory sizes. And now, what is the main significance of these segment registers here? What is the purpose of segment registers, and for what purpose we are using these segment registers in 8086? So as I said that the segment registers are 16-bit registers. So they are the 16-bit registers. The segment registers are 16-bit registers. So therefore, so they can store a value of 4 zeros to a maximum value of 4 Fs they can store. In a 16-bit register, you can store a minimum value of 4 zeros and maximum value of 4 Fs. Okay. So here the segment registers are mainly, it is used to hold the upper 16 bits of the starting address for each segment. Hence, this upper segment address is called the segment base address or simply segment address. Segment base address or simply it is a segment address. So see, in the previous point, we discussed that within the 1 MB of the memory space, the processor is defined 464 kilobytes of the memory. So now to point out that those 64 kilobytes of memory, 464 kilobytes of memory, we need 4 memory pointers. So now the segment registers here, they act as a memory pointers for all these 464 kilobyte of memory. So that's why we have assigned they are named with the same name of the segment registers: code segment memory, data segment memory, stack segment memory, extra segment memory. So which means that the code segment register, it acts as a memory pointer for code segment memory. Data segment register acts as a memory pointer for the data segment memory. Stack segment register, it acts as a memory pointer for the stack segment memory. And extra segment register, it acts as a memory pointer for extra segment memories. So the segment registers, they act as a memory pointer and they are used to hold the upper 16 bits of the each starting address of the segment blocks. So therefore, so these addresses are called segment base address or the base address or simply segment addresses. So to easily understand, the segment registers are used to hold the 16-bit base address, 16-bit segment base address. Okay. So the next one is the instruction pointer register. So what is this instruction pointer register? So here the instruction pointer register is also a 16-bit register. The instruction pointer register is also a 16-bit register. And this instruction pointer register, it consists the offset address. It consists the 16-bit offset address. 16-bit offset address. So the other name to this offset address, which is also called as the effective address. So the instruction pointer is a 16-bit register which is used to contains the offset address or effective address of the next instruction. So generally the instruction pointer refers the offset address of the next instruction which is going to be executed. Okay, so simply it holds the 16-bit offset address or effective address. And the third unit here is the address generation unit. So far we discussed the segment registers and instruction pointer register. So segment registers are the 16-bit registers. They are used to hold the segment base address, upper 16 bits of the segment base address. And the instruction pointer is also a 16-bit register which is used to hold the offset or effective address. So which means that segment registers holds the base address and instruction pointer register holds the offset or effective address. So now, what is this address generation unit? So here the address generation unit, it generates the 20-bit physical address from the segment base address and effective address. Actually, the real address of the 8086 processor is 20-bit because we have 20 address lines A8 to A19. Isn't it? The 8086 has 20 address lines. So therefore, with these 20 address lines, the range of the memory that can be accessed by the processor is, it can access with the minimum address is 0000 zeros and the maximum address location is 5 Fs here. 5 Fs here. 5 Fs. So this is the range of the microprocessor. So we have 1 MB of the memory space. That 1 MB of the memory space can be ranged into 5 zeros to, it can be ranged from 5 zeros to 5 Fs. The minimum address location is 5 zeros. The maximum address location is 5 Fs. So now, to have this 20-bit physical address for 8086, we require two 16-bit addresses here. So they are segment base address which is provided by the segment registers and effective or the offset address which is provided by the instruction pointer register. Therefore, to generate a 20-bit physical address or 20-bit logical address for processor, we require the two 16-bit addresses. That is the advantage with the 8086 architecture. So using the 16-bit address, you are organizing the 20-bit memory, 20-bit address memory. So that is the advantage with the 8086 processor. So how the 20-bit physical address is generated by the address generation unit. So here the segment address. So the segment address is provided by the segment registers. Core segment, stack segment, extra segment, data segment. So these registers provides the segment base address. So this segment base address is logically shifted left by 4 times and that is added to the offset address. So if the segment base address contents are shifted logically left by 4 times and it is added to the offset or effective address of the instruction pointer register, then we will get the 20-bit physical address. We will take an example and we will see that. Okay, but the point is how the 20-bit physical address is generated for the processor. In order to generate the 20-bit physical address, we require the two 16-bit addresses. So they are segment base address, which is provided by the segment registers, and effective or offset address, which is provided by the instruction pointer register. So if you have these two 16-bit addresses, then you can generate the 20-bit physical address. So how we can generate? The segment base address is logically shifted left by 4 times, and if it is added to the offset address, then we can determine the 20-bit physical address. So you can also see the same point in a pictorial manner. If you see in a pictorial way, so we will have the 16-bit address offset value or the 16-bit offset address, and similarly we will have the 16-bit segment address. So now if you shift the segment address left by 4 times, which means that so you will append a 0 on the right hand side. So therefore now it becomes the 5-digit number. And now if you add this offset to that shifted segment address, so you will get the 20-bit physical address here. We will get the 20-bit physical address. So from the offset address and the segment address, we will generate the 20-bit physical address. So the segment address is logically shifted left by 4 times, so that the bit position is shifted by left by 1 bit position. And now if you add the offset value or the offset address to that shifted address value, you will get the 5-digit of the 20-bit physical address. So to understand this, we will take so first how to represent the 20-bit physical address here. The 20-bit physical address or the 20-bit logical address is represented as segment offset. The segment refers the segment base address, offset refers the offset address. So the physical address is obtained by shifting the segment base address 4 bits to the left and adding to that offset address. So which we have already discussed the same point. So we are again I am discussing. So now here take an example here. So the 20-bit physical address is represented with the two 16-bit addresses. And how to represent the two 16-bit addresses? Segment offset. So here we have two addresses, 16-bit addresses. This is the first 16-bit address and this is the second address. So the left side refers the segment address and the right side address refers the offset address. So now what we have to do for generation of the 20-bit physical address? The segment address. So what is the 16-bit segment address? This is A4FB. So now if you shift all these 16-bit addresses bits left by 4 times, you will have a bit position change. Actually previously the bit position is at here. So now by shifting left by 4 times, now the bit positions are changed to A4FB with an appended of the 0. So now previously it is a 16-bit. By shifting now it is now become as a 20-bit physical address. So A4FB0, and now we will add the 16-bit offset address. What is the 16-bit offset address? 4872. So 4872. So now if you add this, you will get a value of a 20-bit physical address A9822. See, so this is now the 20-bit logical address, the 20-bit physical address for 8086 processor. Remember, this concept is very important. So how to generate the 20-bit physical address? In order to generate the 20-bit physical address, we require the two 16-bit addresses. So one is segment base address and the other is offset address. The segment address is logically shifted left by 4 times, so that you are changing the bit position values. And now if you add the offset address directly to that value, you will get the 5 digit. I mean that 20-bit logical address you will get. Okay, so hope you understand this. So this is about the address generation unit. So simply the address generation unit is used to generate the 20-bit physical address for 8086 processor. And the next part in the bus interfacing unit is instruction queue. So what is this instruction queue here? So here the instruction queue is nothing but it is a group of registers which is work based on the first in first out principle. It is nothing but the instruction queue is nothing but a group of registers. Okay, and they will be working on the principle first in first out, which means that so the first you get into the queue, so it is the out from that instruction queue here, the first in first out service. And what is the size of this instruction queue? As I said that it is a group of registers. So how many registers are there for this instruction queue? So the size of this instruction queue is 6 bytes here. So you can observe this instruction queue in the architecture diagram also. You can observe in the architecture diagram also. Okay, 6 byte of the instruction queue. So here the bus interfacing unit fetches the instruction codes and they will be placed in the instruction queue. They will be placed in the instruction queue. So whatever the prefetched instructions or the data from the memory or input device, so they will be placed in the instruction queue by the bus interfacing unit. And here the execution unit, it receives the instruction codes from the queue and it executes the instructions and it stores the results in the general purpose registers. It executes the instructions and it stores the results in the general purpose registers here. So here the instruction queue, so it bridging the or it connects the bus interfacing unit and execution unit, because the bus interfacing unit, it fetches the memory, it fetches the instruction codes data from the memory, and the fetched data, it is placed in the instruction queue, where the execution unit, so it takes the instruction codes and data from the instruction queue. So therefore the execution unit and the bus interfacing unit, they work independently. They don't depend on each other. They depend on instruction queue. Okay, so continuously the bus interfacing unit fetches the instructions, and where the execution unit, it receives the codes from the instruction queue for the execution. Okay, it is a continuous process. As long as you run a program, as long as you execute a program, as long as you run a program, or as long as you execute a program, so this is a continuous process in the instruction queue. So that's why here the architecture of the 8086 is also mentioned as pipeline architecture, because the execution unit and bus interfacing unit, they don't depend on each other, but they work independently each other. So that's why it is a name that pipeline architecture here. Okay, so this is instruction queue. So in a simple way, the instruction queue can be defined as, so it is a group of registers which works on the principle of the first in first out, and the size of the instruction queue is 6 bytes. And the prefetched instruction data are placed in the instruction queue by the bus interfacing unit. So this is about the instruction queue. So did you understand this? And the another functional unit in the bus interfacing unit is another functional unit from the bus interfacing unit is, from the bus interfacing unit is bus control logic. So here the bus control logic unit, it generates uh, the required bus control signals for 8086. Okay, it generates the required bus control logics. So what are the bus control signals here? The various control signals are the memory read, memory write, IO read, and IO write. So in order to generate these four control signals, memory read, write, IO read, and IO write, so here the bus control circuit consists the necessary logic circuitry, and which generates the bus control signals such as the memory read, memory write, IO read, and IO write. So this is about the bus control logic. So this is all about the bus interfacing unit. This is all about the bus interfacing unit. So in the bus interfacing unit, so we have discussed segment registers, instruction pointer register, address generation unit, and then instruction queue and bus control logic. So these are all the functional units in turn of the bus interfacing unit. So hope you understand this. So if you have any doubts, you can ask me. Okay, so you can ask me at any time. You can ask me at any time. And as we discussed about the instruction queue, so let's go back to the architecture diagram and have a look here. This is the instruction queue here. This is instruction queue, this one. See, so which is nothing but a group of flip-flops. Sorry, it is nothing but a group of register, because the register is group of flip-flops, right? So here the instruction register is a group of registers, and it is a size of the 6 byte. So it is a size of the 6 byte. So in each register you can store a byte of information. So the bus interfacing unit fetches the instruction codes and data of the program, and they will be placed in this instruction queue. And the execution unit, it receives those instruction codes and data from the instruction queue, and they will execute. So that's why I'm telling that the architecture of the 8086 is a pipeline architecture, because the bus interfacing unit work independently and execution unit work independently. You have separate functions for the bus interfacing unit and execution unit, but these two depends on the instruction queue, because the execution unit gets or receives the data from the instruction queue, but the bus interfacing unit, it fetches the data and the codes, and they are placed in the instruction queue. Okay, on instruction queue they depend, except that they will work independently here, the bus interfacing unit and execution unit. So with this I am concluding for the 80 architecture. So in this class, so we have discussed the 8086 architecture. In that architecture, so we have discussed the bus interfacing unit. About the bus interfacing unit we have discussed. Okay, so with this I am concluding for today's session. Thank you all.